Hello everyone, in this video we are going to discuss the IGCSE past paper questions on the topic waves. So we have 3 videos on discussing the IGCSE past paper question. This is your video number 1 where we'll be taking up 3 questions, question 1, 2 and 3. In the next video we'll take up more and more questions. So let us start with question number 1. Let us understand question number 1. The figure here shows a scale drawing of plane wave fronts approaching a gap in a barrier. So you have a barrier, you have plane wave fronts approaching the barrier. Okay, so part A of the question says, draw the pattern of wave fronts after the wave has passed through the gap. You have to draw the pattern on the other side of the gap. It's a 2-mark question. Please be careful. That means the examiner is looking for 2 valid points in your answer. Draw diffracted wavefronts like this. At least 3 or 4 wavefronts you should always draw in your answer, right, to get one of the points, and to get the other point you have to make sure that the wavelength is not changed. Say that the spacing here visually, if it looks like to be say 1 centimeter, you should make sure that the spacing on the wavefronts after the diffraction is also approximately 1 centimeter. You do not have to use any ruler or anything. Just by the look of eye, if it looks like you are not changing the wavefront, you will get the other 1 mark as well. If you want, we can look at the mark scheme as well. Sorry, this is the mark scheme for question number 1. Question number 1, the mark scheme for part A. Clear attempts at semicircle, at least 3 diffracted wavefronts they want to look at, for which you get 1 mark. Same wavelength as the incoming wavefront by the look of the eye. You do not have to use the ruler. Another point, if you are drawing the diffracted wavefronts as something like this, if your diffracted wavefronts are like this, clearly by the look of the eye you can clearly see that the wavefront, the spacing between the wavefront has decreased. That's a wrong answer. Spacing between the wavefront on both sides of the gap should be the same by the look of the eye. Then only you'll get both the 2 marks in this question. Alright, so this is understood. Let us come to the part B. The wavefront approaching the barrier has a wavelength given to you. The wavelength is given to you, the speed is given to you, calculate the frequency. Now this is simple. You use the wave equation, V is equal to F times lambda. So how much is the frequency? Frequency is V over lambda. You know the velocity, the units are the same, so you need not change anything to meters. Here also you have centimeter, here also centimeters, so we can work with it. Centimeters and centimeters in the numerator and denominator, they'll cancel out. So you have 20 as the speed and 2.5 as the wavelength. When you'll divide them, you'll get your answer. If you see, look at the mark scheme. Speed divided by wavelength, 20 over 2.5. This will give you your answer, which is 8 Hertz. 20 divided by 2.5. 8 Hertz. Simple and easy question. Let's come to the C part. State what happens if anything to the frequency of the wave as it passes through the gap. So they are saying what is the frequency on the other side of the barrier. Now this is something that we have done in the theory of waves. What did we do? That the frequency is a factor which does not change in diffraction. Not only diffraction, the frequency doesn't change in reflection and refraction as well. So if you have not gone through the theory videos, go through it. Everything is mentioned about these things in the theory videos. So the frequency, what do you say? Frequency does not change. Let us tally our answer with the mark scheme. The candidate said if it is the same as 8 Hertz, you get full marks, or you say nothing happens to the frequency, you get full marks. Right? So nothing happens to the frequency or the frequency does not change is the correct answer. Explain in terms of diffraction why a car radio may pick up low frequency radio signal but not pick up a high frequency radio signal when the car is traveling behind a hill. So this question is all about diffraction. If you have not gone through the theory on diffraction, go through my theory video on diffraction. You'll find the answer to this question as well there. So what is happening? Low frequency radio signal, high frequency radio signal. Let us understand how a low frequency radio signal will look like. Low frequency, lesser number of waves. Low frequency, lesser number of waves in a given period of time. That's a low frequency. High frequency, more number of waves in the same amount of time. So second picture is a high frequency because you see larger number of wave patterns in the same amount of time. The amount of time is the same. The amount of time, the spacing is the same. In the low frequency signal, only 2 wave patterns you see, and in the second picture you see a lot of waves being present in the same amount of time. Where do you have high wavelength? You have higher wavelength in the low frequency. Low frequency means high wavelength, high frequency means low wavelength. Right? So be clear. So what should you be writing in your answer? Low frequency means high wavelength, high frequency means low wavelength. So what happens? If you remember, one of the fundamentals of diffraction is that more is the wavelength, more the waves diffract. Let me write the answer. More is the wavelength, more is the diffraction. This is done in the theory part. More is the diffraction means more is the scattering of the wave. Right? Low frequency signals have high wavelength. Low frequency signal has high wavelength. So this should be your first point. Low frequency signal has high wavelength, and more is the wavelength, more is the diffraction. So more is the diffraction means more is the scattering. Therefore, there is a high likelihood that the radio antennas will catch the low frequency signal. Why? Because low frequency signals are scattered more all around in the environment around us. Therefore, there is a high likelihood, high chances that these signals will be picked up by the radio. So explain in terms of diffraction why a car radio may pick up a low frequency signal but not a high frequency signal when the car is traveling. Why? Because low frequency signal has high wavelength. More is the wavelength, more is the diffraction. We have given 2 valid points and it's a 2-mark question. You'll score full marks in this question if you write your answer this way. If you give 2 valid points, you'll score full marks here. Let us look at the mark scheme as well. Low frequency signals have longer wavelength. This will fetch you 1 mark. Or you can also say higher frequency have shorter wavelengths, other way around. Either of the things you can mention. So therefore, low frequency signal, longer wavelength signal, they diffract more. 2 points, 2 marks. Alright, so question number 1 is done. Let us come to question number 2 now. You may pause the screen on question number 2, attempt the question yourself and come back to validate your answer. Please pause the screen. So I hope that you all have solved this question now. Let us look at the solution. A water wave in a tank travels from a region where the speed of the wave is faster to a region where it is slower. Now figure this is a 1/4 scale diagram, shows the wavefront in the region where the speed is faster. So here the speed is faster. Take measurement from the scale diagram, determine the wavelength of the water wave as it travels in the faster region. So here the question asks you to use your ruler. You have to use your ruler and measure the spacing between the wavefront. Right? This diagram, this picture is not to scale, but in the examination, the real picture, the spacing between the two lines, consecutive two lines that you see here, is actually somewhere 6 mm to 7 mm. If your answer is coming out to be 6 mm to 7 mm, so that's what the mark scheme says is the correct answer, right? So it will come out, say, let's work out with some number between these two, and then you'll have to convert it to scale. Finally, let's say that the wavelength, let's work with the wavelength which the mark scheme tells us here, so that the validation of the answer becomes easy for us. The mark scheme henceforth works with the number 26 mm. So let us say that the wavelength comes out to be 26 millimeters. Right? This is quite a subjective question to start with, because the measurement depends on having the actual copy of the question paper, which we do not have. So the first answer will directly pick up from the mark scheme, which is 26 mm, right? And rest of the calculations will be based on this number. All right. The speed of the wave in the faster region is given to you. In the faster region, the speed is given. Calculate the frequency of the wave. In the faster region, you know the wavelength, you know the speed. You can calculate the frequency by using the wave equation. Wave equation says V is equal to F times lambda. You know the speed, input the value in the speed. You know the lambda, input the value in the lambda, but make sure that you're inputting the value of lambda in terms of SI unit. SI unit should be in meters, right? So frequency will be speed, which is 0.39, divided by lambda, which is 0.026. Divide these two numbers and you should get your answer. You'll have to work it out in the calculator. Let's look at the mark scheme. They have also done the same thing, and the speed and the frequency will come out to be 15 Hertz. If you look at this question, it's a 2-mark question. So always a good practice to follow is that you start with the formula. Either you write the formula this way or this way, you get 1 mark for that and the other mark for the correct answer. If your answer is not correct finally, but if your formula is correct, you'll still get 1 mark, right? So that's why it's a good practice to write the formula. So the answer should be 15 Hertz. Now B part. Draw lines that indicate the position of the wave fronts of the water wave in the slower region. Now this thing is done in the refraction and the reflection of the wave fronts. Please check out my video on the theory of this, and this is very clearly done. You should be able to understand it when you go through the video. So how will the wave fronts turn? They will bend towards the barrier. The wave fronts are going to bend towards the barrier. Why? Because they are entering a region of shallow region, or they are entering a region of slower speed. They are entering a region of shallow speed. So for each of the waves, you have to draw them bending towards the barrier, and they have to be parallel lines, as you all can see here. It's a 2-mark question. The examiner will be looking for at least 2 correct points. So you have drawn the parallel lines for each of the wave front. That fetches you 1 mark plus another mark for showing a bending towards the barrier. This is your barrier line. All right. If you see, the angle with the barrier is going down. Earlier the angle was with the barrier was this much high, now it has gone down, decreased. Angle with the barrier will decrease. Another point for showing the band bending towards the barrier. If you look at the mark scheme also, it also says the same thing. At least 4 wavefronts showing refraction in correct direction, and 7 wavefront lines continues with those in the faster region. So if you can draw all the 7, 1, 2, 3, 4, 5, 6, 7, you get one of the points. Another point for showing the correct bending of the light. C. State what happens to the frequency of the water wave as it passes into the slower region. What is happening to the frequency? 1 mark question. You have to just state frequency. Please do remember we have discussed it during the last part of the diffraction video in the summary section. The frequency is a factor which does not change neither for reflection, refraction or diffraction. So you can say frequency does not change. If you see this question is repeating, this question is solely on refraction. This whole question is on refraction. The answer is frequency does not change. The previous question, question number 1 that we solved, it was on diffraction. Here also they asked about what happens to the frequency. The frequency does not change. If a question is on reflection also, then also the frequency does not change. Remember, at reflection, refraction or diffraction, the frequency never changes in any of these 3 phenomena which you have to study for your exams. Let us come to the question number 3. Now this question is on reflection. Sound from a speaker is traveling in air towards a solid wall. Sound is traveling. This is your wall. The figure shows compression of the incident sound waves and the direction of the travel of the wave. So these lines that you see, these standing lines are the compressions, and here this arrow shows the direction in which these wavefronts are traveling. What is meant by the compression? Simple and straightforward. They are region where the molecules are close together. This is also discussed when we were talking about transverse and longitudinal wave. For this section, the theory is done in transverse and longitudinal wave. Question is very common. How do you define compression? High pressure area, or you can say, or else increased molecule or particles are close together. High pressure, increased pressure, or molecules are close together, high density. All right. Let's come to the next part. The distance from P to Q is given to you 8.5. It takes 2.25 milliseconds for the compression at P. Compression which is at P to reach at Q, the time is also given. It takes 25 milliseconds. The distance between them is given. The time between them is 25 milliseconds. For this sound wave, determine the wavelength. What is the wavelength? Wavelength, when you are given the wavefronts, it is the distance spacing between the consecutive wavefronts. This is your wavelength. If you do not know how to find the wavelength when you are given the wavefronts, go through my theory video on waves and wavefronts. Right? So this is your lambda, another lambda, 3 lambdas, 4 lambdas and 5 lambdas. 5 lambda of a distance is 8.5. 1, 2, 3, 4, 5. 5 lambda is equal to 8.5. So lambda is how much? 8.5 divided by 5. So 1.7 meters. That's your answer. Let's tally our answer. Yes, it is 1.7 meters. Let's come back to the question. How much is the frequency? How much is the frequency? Let us write the word. How do we start this question? V is equal to F lambda. So F is V over lambda. Alright. So what is the speed of the wave? What is the speed? Speed is distance over time. How much of a distance is traveled? 8.5 distance is traveled in how much of a time? 25 milliseconds. So it is 8.5 over 25 times 10 to the power minus 3. That's your speed. Let us input the value in the formula. 8.5 divided by 25 times 10 to the power minus 3. This is your speed over 1 times 1 over lambda. How much is the lambda? 1 over lambda you have already calculated here, 1.7. So this whole thing goes 5 times. So 5 here, 1000 over 5. Let's tally the answer, 200. Right? We know that this thing will go up. So this becomes 1000 over 5, 200 hertz. Alright. So C part, I would highly recommend that whenever we start a question, you should pause the screen, solve the question yourself, and then play the video to tally your answer. Even if I forget to say that, do it yourself. Pause the video, look at the question, solve it yourself, and then play the video again. As it strikes the wall, the sound reflects. Complete figure this to show the position of 3 compressions of the reflected wavefront. Now reflection of wavefronts also is done. You may refer to the reflection of wavefront to find how to find the reflected wavefronts. So let us complete this. So that's how the wave travels and hits the wall. Let us now draw our normal at this point where it hits the wall. This looks like your normal 90 degrees. You'll have to use your protractor. 90 degrees. Let us now draw the reflected wavefront. Let me use red color to draw the reflected wavefront. This not the reflected wavefront, I'm sorry, reflected wave. This is your reflected wave. It is a step-by-step process, and all the steps for the reflected wavefront, how to construct the reflected wavefront, is shown in my video on reflection of waves. Go through it. So you know the incident wave. Make it hit the wall. At that hit it point, draw the normal. That's your normal. The green line is your normal. Use your protractor to find the angle of incidence. This is your angle of incidence. Make the corresponding angle of reflection. Both should be equal. I is equal to R. If I is say 22 degrees, R should be 22 degrees, same angle. You have got the reflected ray. Reflected ray. Now you have to find the reflected wavefronts. Reflected wavefronts will be perpendicular to the reflected ray. Reflected wavefronts perpendicular, they will be perpendicular, and the spacing between them will be same as the incident wavefronts. The black lines are your answer. These are your reflected wavefronts. This, and this. Waves and wavefronts are waves. The red line is your wave, reflected wave. The black lines are your reflected wavefronts. They have to be perpendicular to each other. This is something, please go through my videos on wave and wavefront, and as well on the reflection of wavefronts to understand how this is done. It is a step-by-step process and very easy process. If you go through the video, you'll understand it very well. So these black lines are your answer. Let us go through the mark scheme. For C, it's a 2-mark question if you see. 1 and 2. How do you score the 2 marks? 3 compressions at least, which should be 23 to 33 degrees through the wall just by the look of the eye. Constant and correct wavelength. Constant and correct wavelength, that means the spacing before, the spacing between the wavefronts before should be equal to the spacing between the wavefronts after the reflection. Alright. So this is done. Let us move to the last part, which is D part. The loudspeaker is immersed in water. It continues to produce sound of the same frequency. Frequency is not changing. State and explain how the wavelength of the sound wave, this is the question, in the water compares with the wavelength determined in this part. As compared to this, how the wavelength is going to be. Simple and easy. This is also discussed in one of my theory videos. It comes from your V is equal to F lambda, and that theory video is on reflection and refraction. Frequency is static, not changing. What happens to the speed in the water? Speed in the water is more than the speed in the air. Why? Because water is more dense. Water is a high density region, so the speed of the sound in water is high. If the speed goes high, what happens to the wavelength? Wavelength also has to increase so that the right hand side of the equation stays equal to the left hand side, because the frequency is constant. Whenever the speed increases, the wavelength increases. Whenever the speed goes down, the wavelength goes down. It is explained using the wave equation. So what do you say? You write this whole equation, V is equal to F lambda. Then you say, because V is increasing, let me use an upward arrow, you write it fully, V is increasing, so lambda will increase. So that, why? So that the wave equation holds true. All right, let us look at the mark scheme as well. Higher wavelength should be the ultimate conclusion. Wavelength is going up, for that you'll get 1 mark. Why? Because the change of the speed is correctly related to the change of the wavelength. How do you show this correct relation? By using the wave equation, V is equal to F lambda. Alright, so this was the end of our video number 1. In the next video, we'll take up 3 more questions, question number 4, 5 and 6. That will be in video number 2. Video number 3 will take up other 3 more questions.